Alrighty, in this video, in the last video, we discussed what the current paradigm of the genetic code is. I think I gave it a pretty fair telling. That is how it's told. Um, and in this video, we're going to discuss why this is the worst scientific paradigm in the history of science. And it must go. And the reason why it's so bad, never mind the fact that they ignored every, tenet of logic and math and science. But the reason why it's so bad is because it's it, everything it says is false, and so in order to fix it, all we have to do is say the opposite, and that's a good sign that it needs to go. I mean, if you can, if you can't say anything true with a paradigm, but you can say true things by saying the opposite of the paradigm, then that's a pretty good sign. I've lost my pen. I must have taken it anyway. So this video could take days or weeks. I'm going to try and do it quickly. I'm going to go down this list of things that they said. The genetic code is the codon table. That's just stupid. Okay, that's you can't say that. Okay, it's not a recipe. It's a code. It's simple, linear, and deterministic. Okay, now this gets to the heart of it. The code of all life, the genetic code, is the most complex thing in the universe. Okay, that's just a fact. All right, linear. No, it's the most non-linear thing in the universe. Deterministic. No. This is not based on, it's not like sockets and plugs where this determines this. This is based purely on probability. This is what information is. Okay, we're going to talk about information later because we have to. They don't understand information. Information is making choices of things that have qualities. In other words, what is the probability of this choice versus that? So to say it's simple, linear, and deterministic is just false. It is complex, nonlinear, and probabilistic. Okay, 4 nucleotides, 20 amino acids, 64 codons. Okay, that's just stupid. You could say there's only 4 nucleotides and 20 amino acids, but that's false. So if we look at these sets, okay, there's 4 nucleotides in DNA. There's a different nucleotide in RNA, mRNA, and then in tRNA, there's another nucleotide, so that makes 6. And then I think, I don't know, they found 21, 22, at least let's say 22 amino acids. So now, if we just use their math, we get 64 codons here. We got to add 32 codons here. Now we're using, instead of using triplets of 4, we're using triplets of 5. So technically, it's 125. But the reality of it is that we're not limited to just these nucleotides. So we already have hundreds of codons just to describe. We needed a codon table for the double helix. So one of the strands is a codon. That means the other strand is an anticodon. So we need a table for that. Then we need a codon table to go from DNA to mRNA. So there's second codon table. Then we need another codon table to go from mRNA to tRNA. So now we've got literally hundreds of codons, and we've got an unknown number of nucleotides, and we don't even have binary pairing rules anymore. We're starting to introduce new pairing rules along the way. So to say that there's, what did we say? We said 4 nucleotides, 20 amino acids, 64 codons. That's empirically false. It's logically incoherent. You can't say it. So I think one of the greatest ironies, one of the greatest ironies in this story, one of my favorite ironies, is that Gamow, who invented the codon table, he's the inventor, the concept of a table that is codons. He came out with this codon table and they rejected it. Okay, this is the most right codon table they ever had, because you can't, a codon is a variable, all right? You have to define your variables. So what he did was he says a codon is a set. And a codon table is a set of sets. So he made these 20 codons, a set of codons, sets of sets, cyclic permutations, all that bullshit. Okay, so that was exactly right. And if they would have bothered to test it, they would have found that he was right. So what he actually did was he made this prediction with this table. He predicted when we get this code, it's going to fit into this table. Well, he was right, but he was right in reverse. So he predicted 20, the assignment of 20 codons, or 20 triangles. And he predicted the assignment of 20 amino acids. And they failed after 2 or 3 codons, but they didn't ask how they failed. So every single triangle failed his prediction, because he predicted that there would be one and only one amino acid in every triangle, and that amino acid wouldn't be in another triangle. So that's false for every triangle. Every single amino acid failed. He predicted that it would be in one triangle and only one triangle, and that's false too. So he goes 0 for 4. He goes 0 for 40, which is really hard to do. So his failure was perfect. Okay, it's almost as hard to perfectly fail as it is to perfectly succeed. The number of possible scenarios for a codon table exceeds the number of atoms in the universe. So the chances of being right are astronomical, but the chances of being wrong are also. So it's called proof by contradiction. This is a mathematical proof that this is actually a valid codon table. This defines codon tables. These are what codons are, and you can't find any of them on that table. So this codon table has no codons. They use the actual values, the molecules, to define their variables. Well, that's just stupid. You can't do that. That's not how codes work. So what you got to do, they said there's 64 codons here and there's 20 amino acids here, but that's false. So what you need is a variable. And so this variable has to take these values. So call it a codon. The codon takes the value of the DNA, and then it substitutes the value of the mRNA, and then it substitutes the value of this, and then it substitutes the value of this. So the variable itself, the codon, has many values. It's nonlinear. So if you define your codons properly, the best optimized number for them is 20. There's 20 codons. And it's a set, and they're symmetrically related, and that's how codes work. And so they didn't do this. They just logically incoherent description. When we talk about the actual real codon table, later we'll talk about how that actually works mathematically. But Gamow was right. He was smart. They just never tested it and proved that he was right, but they could have. Degenerate, that's just ridiculous. There's not more information in DNA than there is in protein. Is there more information on your cell phone, the video file, or the video? Well, that's how things work. It's compressed in DNA, and there's an algorithm, a fractal decompression algorithm, that decompresses it into protein. There's vastly more information in a protein than there is in the DNA that encodes it. Arbitrary, this is the least arbitrary thing in the world. The only reason they thought it was arbitrary was because they used a mathematically incorrect graph. If you take a mathematically correct graph, the last thing in the world that you say is this is arbitrary, this is perfectly symmetrical, it makes a lot of sense. These assignments create a coherent pattern. The only reason they thought it was arbitrary was because they analyzed the data with the wrong method of analysis. Functional imperative, that's the dumbest thing I've ever heard. Life is evolution. The genetic code is life. To say that the genetic code can't evolve, that should be disqualifying. That's just stupid. A frozen accident. It's not an accident. It's not frozen. One-dimensional molecular information. Who in the hell? What is wrong with these people? Okay, I got these molecules here. I've already forgotten what their names are, but let's just look at them. Okay, this is what a molecule is. So what it is a collection of atoms. It's this semi-permanent arrangement of atoms. Okay, So these are 3 nucleotides, and I'm just going to say they're A, C, G. ACG, so that's a codon. And then that will be assigned to this amino acid, threonine. And we can see right out of the gate that these codons are ginormous compared to the amino acids. And then in the middle of this stuff, these tRNA, I mean, there's 3 for the codon, but there's like, I don't know, 100 for the tRNA. The tRNA is ginormous. How you ignore that, I don't know. I don't know how they do any of this. It's superstition. They just say we're going to close our eyes and it's going to all take care of itself. Okay, so what we got to know about a molecule is that it's a set of atoms. So it can be any kind of set of atoms. So that doesn't tell us what the molecule is, because these atoms have to be connected in space. Okay, so now we got 2 things. The molecule is defined as a set of atoms that have bonds. Okay, that's what a molecule is. It's a structure. The information of a molecule is its structure. Now, the information of its atoms is a subset of that structure. So there's more information in the structure than there is in the atoms. Just knowing the atoms doesn't tell us the structure. But if we know the structure, so this is a structure, this is a structure, this is a structure. So now we've got 3 nucleotides. The 3 nucleotides together are a structure. So we know the structure. Now we can determine the sequence. We can say, oh gosh, ACG. The sequence is ACG. That was determined by the structure. Okay. Now this is always true. This is not a theory. This is a fact. It's always true that a sequence in a molecule, any molecular sequence, is always determined by its structure. So to take a logical fallacy and use it as an explanation for an idea, that should be disqualified. Sequence determined structure is moronic. That's false. It's logically false and it's empirically false. So that should be a red flag. We can't do that. That's just stupid. And then to take that and create the homunculus that, since molecular information is linear, the genetic code is linear, that's just the world's greatest homunculus. There's so many homunculi embedded in this paradigm. It's unreal. They make every possible mistake. The thermodynamic hypothesis, nice try, but no. The protein can fold in many different ways. One way we can know that, if you take a sequence of nucleotides and it creates a sequence of amino acids, then that protein will fold up in one way and one way only. We can change the nucleotides, make mutations in the sequence called silent mutations, keep the amino acid sequence the same, and we can get a different folded protein. Okay, so now one sequence of amino acids can fold in at least 2 ways, and it is determined by the sequence of nucleotides. So that means that it can't be sequence only. This just empirically destroys the entire idea of a one-dimensional code. It's empirically not a one-dimensional code. You can't do it with just sequence information. So what's the next step? Well, if we can't remove all the spatial information from the code, maybe what we should do is put it back in, because that's what it is. It's a spatial code. Molecules are spatial things. Then we go on. So one gene, one protein. Well, that's just, it's hard to explain just how dumb that is. But we'll, all right, well, let's just try. Let's try and explain how dumb that is. All right. All right, this concept is we take the double helix, we find a gene in there, and then we make a protein out of it. There's one gene and there's one protein, okay? This is just the most false thing you could ever say, because this double helix, there's two strands. Okay, so for the very first thing you have to pick is a strand. So now the probability of a gene is 50-50. It could be this strand or that. Then you have to come up with a reading frame. So in other words, it could start here and go to here, but it could shift backwards one, or it could shift forwards one. So now we're starting to come up with multiple ways to, I mean, we don't even know which of the three is a codon, let alone the gene. So then you transcribe it into an mRNA. Well, this son of a bitch gets chopped up into introns and exons, and then it gets re-spliced together. So to say that we're going to take one thing out of here and create one thing over here, that's just insane. And we already know that it can fold in many, many ways. So we haven't even discussed just exactly how many things might be this protein. Okay, what they're doing is they're flipping cause and effect on its head. Okay, they're looking at the result of what they're testing, and they're saying that's the cause of it. That's just insane. The reality of it is there's many, many, many possible genes, many, 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 many more possible proteins. So there's a probability of a gene, and there's a probability of a protein. Now, in between the gene and the protein, we already know that there are all these other steps. Well, this is the code. These molecules in between these steps, they're real molecules. You can't ignore them. That's the machine. It's a machine language. You got to include all the parts of the machine. You can't just say we're going to ignore DNA, or we're going to ignore RNA, or we're going to ignore tRNA, whatever. That's just wishful thinking. That's a superstition is what that is. Now, so this whole idea of one gene, one protein. The other thing is this. I mean, if this is a codon, and this is an amino acid, it's just false to say that there's one codon for one amino acid, because empirically, we know that in our own bodies, I think it's A, U, A, it's isoleucine, I think in the cytoplasm, but in the mitochondria, it's methionine. So in this case, we've got one codon and two amino acids. And, you know, there's all kinds of demonstrations of alternative codon tables and all that. Okay, so it's not one codon equals one amino acid. And then the silent mutation thing shows us that there's something besides the amino acid. So now we need to think about two codons, and this bond between these two amino acids is called a peptide bond. So what the code is really doing, more than, you know, one codon equals one amino acid, it's doing two codons equals a peptide bond. So it's not really a code of one codon. That's the sound of one hand clapping. It's like one neuron, you know, it can't fire, it has to have two neurons. So what we need to start doing in terms of just the basics of this code is start thinking about a two codon code. You know, we need to have an amino acid compared to another amino acid. So now, you know, there's 20 amino acids, but, you know, let's say that there's, okay, so then that means that 20 times 20, there's 400 combinations of amino acids. Let's say that there's a chance that there's 10 different kinds of peptide bonds. You know, let's say one of them's kinked and the other one's not. One of them's, you know, fast and the other one's slow. One of them's reliable and the other one's not. So there's 400 pairs here, and then there's 10 kinds of pairs. So really what we're trying to do is capture 4,000 different peptide bonds, not just 20 amino acids. So what the code is actually doing is it starts with the smallest possible sets of things, and then it goes through this translation process where what it's trying to do is keep the sets as small as possible. It's trying to generate larger sets. That's what information is. That's how information works. We'll talk about information later. But it really is a decompression algorithm. It's going from many to many. but the many on the result side is tremendously larger than the many on the cause side. Okay, so let's see. Euclidean, they're hardly using any math at all, but what the math they use is Euclidean. I would argue that this is a homunculus. You can't do that. It's not justified by anything really. It's causing a problem. We got to use non-Euclidean math for sure. They're not describing this as a force of nature, but that's the definition, or at least our definition. They don't even try. It's not universal. We can't think about the origin at a specific place and time. I mean, it's like trying to say that salt, sodium chloride, what's the origin of salt? Well, it wasn't at a specific place and time. We need to start thinking in those terms. It's a process. It's a logic. Anyway, I don't even see why this is necessary to go down this list of idiotic things that they said that are empirically false and logically incoherent. Unfortunately, if you try and tell this to a scientist, they'll do several things. They'll say, oh, well, you just don't understand science. You need to, there's exceptions to every rule. This is too nuanced for, a small brain like yours to understand it. And then they'll try and say, well, this is, you don't understand. You're saying exactly the same thing that we are saying. I'm like, that's just insane. I'm saying something that's radically different. And the reason I'm saying it is because this is radically bad. There's nothing as bad as this ever in the history of science. So anything different is going to be radically different if it's good. And then they try and say that, well, it works. Well, this is positivism. It works for what? Okay, to confuse people, to say a bunch of false statements works for understanding? I don't think it does. I think it works for the experiment for which it was designed. But you make the mistake, this experiment can only do one thing. So, you make this table that can only do one thing. Well, don't assign properties of the real thing, the genetic code, to your table, which is what they did. They got confused. They went out, wandered around, collected things, came back with a flat map. Okay. They said the code's flat and that everything revolves around it. It's like, that's just stupid. Why do you keep repeating these mistakes? But they do. I think this is the worst example of it, but we can find hundreds of examples and they're not that hard to find. It's always the same mistake. It's a recursive argument or a homunculus. And they're everywhere in math and science. So those are the kind of things that we need to keep in mind. And now that we know that this is a false paradigm and it must be rejected, now we can actually have a conversation where we exchange information, where you're not calling me names, which is all they do. They get mad. They get mad really fast. First they get scared, and then they get mad. And then they start gaslighting the hell out of you. They tell you that you're stupid and crazy and you're a heretic. And okay, I agree, I am stupid and crazy and a heretic, but I also happen to be right. So let's back off on the gaslighting a little bit and let's move forward. Now that we know the situation, we can start to set goals as we invent a new paradigm.